to the Boardwalk Talks program, brought to you by the aquarium at the Dauphin Island Sea Lab. My name is Mendel Graver. I am one of the educators here at the lab, and this morning we are going to be chatting with Steve Dykstra, who is going to talk to us about compound flooding, that is flooding from a mixture of sources in the areas, and also about the effects of sea level rise on this flooding. So with that, I am going to let Steve tell you a little bit about his research.
All right, thank you. Yes, so I am excited to share with you about coastal flooding. Currently, about 40% of the world's population lives within about 50 miles of the coast. So coastal flooding can affect us a lot directly, but also because the majority of the world's megacities are located along the coast, and our ports are all located there. Our entire infrastructure and economies are based upon these areas and are threatened by flooding. So at the coast, we have floods that can come from the sea, but we also have floods that can come from rivers. And so where they come together and occur at the same time, they create compound floods. So I want to talk briefly about coastal flooding, and then a little bit about the equipment that I use, and then some of the kind of long-term changes that we can see from flooding. So first of all, coastal Alabama, where we are here at the Dauphin Island Sea Lab. As many of you know where to find Alabama on the map. We're down here where, as you can see, is dark blue. This is precipitation. And so you can see here that Alabama has a lot of annual precipitation here compared to the rest of the country. And Mobile is sometimes called the rainiest city in the continental US. If we zoom in a little bit more to the coast, we can look at the watershed, or the area that basically drains the precipitation. And here we have the Tombigbee and the Alabama rivers, which flow down to the coast. And then for comparison, we have the Pascagoula and the Apalachicola here nearby. And so if we zoom in a little bit closer now, we have the transitional region from the rivers to the Gulf of Mexico down here. And so along this transition, we have tides that come in from the Gulf. We have rivers that flow down. And so as the water flows down from the dams up here, which are about 180 kilometers or 180 miles inland, the tides can actually reach all the way up here during that low discharge, and flooding from the sea can actually affect these regions all the way up here, though the tides take about 12 hours to get up here from the coast. So we are down here at the Dauphin Island Sea Lab at Dauphin Island. So these rivers come together and they flow into a large delta region here, which is this brownish color. And so most people think of the delta as beginning way down here, about halfway, where the Mobile River splits off at the Tombigbee, or to the Tensaw. But actually, the delta begins way up here and is about twice that length. So if we zoom in a little bit more on just the lower delta here, we can see that this region is very low. So this is an elevation map, and so the green and yellow colors show the low elevation. And so when the water levels are high, the entire delta floods. And this entire area is covered by water. So then it basically turns blue from that. And then along this transition, if we kind of zoom in a bit more, we can look at kind of the upper delta area where we have the Alabama River here. And you can see it's It's kind of twisting and turning. We call this sinuosity or meandering. And you see kind of the low areas away from the river. Well, the river actually builds up these areas right next to it, and we call them levees, which actually confine the river. And then when water levels are high, they actually flow over the levees and then completely fill the floodplains quite quickly. And then down at the coast here, we have the city of Mobile over here, where you can see kind of those lines are the streets. And then these are the rivers flowing in. And you can see that it's quite flat, and there's very little change. So we kind of have this big transitional region. And so the topography there completely changes how the flooding dynamics play out near the coast. So as we think about the flooding itself, the flooding that comes from the sea, we can think about it in this bigger map with Mobile Bay and the Gulf of Mexico here. So as it kind of comes in and it rushes into Mobile Bay, it usually occurs because of strong winds, and so these strong winds can create this setup along the coast. And so setup occurs because the wind cannot push the water any further, so it has to rise. And so the waters rise when the wind is strong, and when the wind has a long duration or has been blowing for a while, and also when the direction is in the right direction. Often like for hurricanes against the land. Now, one of the interesting things about flooding is that the shape of the coastline also matters a lot. So if you look at Mobile Bay here, it's much wider down here than it is up here. And in fact, it's kind of like a trumpet shape, or at least physical oceanographers, like myself, we like to call it a trumpet shape. And it's fairly characteristic of estuaries to be like that. And so when the wind blows, it actually has a larger area to blow on, but a smaller area for it to go. And so this causes flooding to actually be higher up at the head of a bay than it does down at the coast. And so this setup, if you think of it kind of rising up, it rises up more here, and surprisingly, an area like Dauphin Island may actually have less flooding than further in, like the Delta area. So the other direction that flooding occurs is from the rivers, and so this occurs because of the precipitation. So flooding can vary depending on the intensity of the precipitation. So basically, how much comes in a short period of time, or the location. So kind of, is it far inland? Is it near the coast? And then secondly, as we think about the watersheds, the watershed can affect the flooding based upon kind of the shape of the watershed. If it's really long and narrow, kind of like the Apalachicola here is long and narrow, so it can take a long time to drain, or the Alabama Tombigbee system, which is kind of larger and kind of comes together. This can cause the flooding to be more intense. And then also the land cover. So basically, if the water falls on a forest or if it falls on concrete, it's going to be very different in terms of the timing that it flows down to the coast. Once the water flows into the rivers, larger events usually flow faster to the coast. But some of my recent work shows that actually near the coast, where the floodplains are really large and wide, the flooding itself and the floodplains, the delta region here in Alabama, acts like a sponge, and it basically soaks up the water. So it kind of slows it down from moving further downstream, and it causes a delay, and it causes the flooding to be less intense downstream, like near the city of Mobile. So then, as we think about the two of them together, where they both happen at the same time. So these kinds of things can happen during like a hurricane, where the hurricane may bring strong winds, and at the same time a lot of precipitation that ends up coming down from the headwaters. And so the time that it takes for the river to flow down the coast is really critical, because this lag time can be long and can keep the flooding from happening at the same time. Or the lag time could be short, and they can happen both at the same time. And when they happen at the same time and they overlap, it raises the water even more and causes these much larger floods to occur. And so the timing of the precipitation events and the lag time can change depending on if we decide to build more levees or to have more flood protection sometimes further inland. What this does is it ends up transferring the flooding that may happen inland, and it basically intensifies it further downstream. So actually what happens inland really matters in terms of the flooding that happens downstream, in terms of how we manage our forests or ditches and such. So enough about these pieces for now. I want to show you a little bit about the equipment that we use to actually measure some of these things. So I'll show you first. This is a drifter here that I built, and you see it has these big sails that go underwater. And then when I put it in the water level is about right there. So most of it is below water, and it can catch the currents. And so it just simply drifts. It doesn't move itself. It just basically catches how the water's flowing. And then inside, I have little GPS units that I keep track of the drifter in. And so I built these little boards that use Arduinos and Adafruit technology that really a lot of people are growing and learning in these days. School kids are finding them really fun and easy to play with. So this is our little GPS unit right there. And then back here we plug into batteries, and then I attach cables here, and these cables go actually down inside, and then down below where I drilled out these holes inside, I have sensors for temperature and salinity. So I can measure how these things change as the water flows. And then you can see that all together. Then over here I have something that's called a YSI 6600, which for short we sometimes just call them conductivity temperature depth sensors, or CTDs. And up here we store a bunch of batteries, and then down here where it's usually protected, we have a sensor for the temperature, and then we have a sensor for the salinity. And so the salinity is measured using conductivity, which is really a measurement of the electricity. So basically, as more salt is in the water, electricity can or a pulse can move more efficiently. And so that's how we measure the salinity. And then also we can measure things like DO and dissolved oxygen and other things on here.
You want to point out the encrusted organisms?
Yes. So after putting instruments like this in the water, we have to clean them off because they quickly get covered by all kinds of little critters that find these hard surfaces as a great home. And so these units actually are out at the ARCO stations that the Sea Lab manages. And so those have to routinely get picked up and cleaned off so they can keep working. Oh, I should also mention these also measure water level using pressure. And then lastly, this unit here is commonly referred to as a ADCP, which stands for Acoustic Doppler Current Profiler. So acoustic basically means like a sound wave, and Doppler, it uses like a Doppler effect. Like if you think of like a sound moving towards you or away, it sounds different. And so it uses that technology to identify how the water is moving, and it can get lots of locations at the same time. So these are great for tracking the currents. So basically this unit is for the currents, and this unit I use predominantly for the water levels at a single station. And then the drifters I can use to track the water as it goes. So together, these make up the primary instruments I use for my work. So lastly, I just want to talk a little bit about sea level rise and the global warming effects. So we often think about them as kind of different things, but in reality, sea level rise is really a response of global warming, because the seas are rising predominantly because not only the air is getting warmer, but also the sea is getting warmer. And so as the sea gets warmer, it actually causes the water to expand. So basically warmer things can take up more space. And so the sea is rising because it's getting warmer. And then in addition, we also have the melting meltwaters from the polar areas too. And so these impacts of sea level rise are causing the waters to be higher, but they're also causing the waters to move further inland. So you might think, oh, I'm up in Jackson, Alabama. I'm really far from the coast. Well, in fact, the tides pass by you. The tides go all the way up to Coffeeville. They go all the way up to Monroeville, and so all the way up there, you can see the effects of the seas rising, and also of the marine influence moving further inland as the seas are rising. This can be in terms of salt. It can also be erosion, or even that wetland loss. And those last two things, erosion and wetland loss, those are actually our flood protection barriers. So sea level rise has kind of like this two-edged sword at the same time. It removes our protection, and it's also rising the water levels. And then the other aspect of global warming to really think about too is that as the air is warming, it can hold more moisture in the air. So if we ever think about a warm day, usually it feels a bit more humid. Well, it's because more more water can be in the air. And so in those warmer days, more precipitation can fall at the same time. So the precipitation is more intense. And so as the air gets warmer, it's actually intensifying precipitation. And so coastally in Alabama here, this is really interesting because in the mid-20th century, the air currents or the atmospheric circulation changed, and so we got more moisture now that's coming in off the Gulf into Alabama here, and so when this change occurred, we can look back and we can see okay, how now has this changed river flooding and also coastal flooding. And in fact, this precipitation intensification has caused the lag time to decrease. So the precipitation events are reaching the coast sooner, as well as the flooding from the rivers is also increasing in terms of how frequent they occur, and also increasing in the magnitude, so the overall water levels. And lastly, as we think about hurricane type of events, compound flooding coming from both places, as we have a shorter lag time from the land it's actually increasing the likelihood of compound flooding as well. So, so kind of pulling this together, as we think about how flooding may affect us, it's not just, it's not the same today as it will necessarily be in 10 years. And so really we need to understand what's been happening now so that we can make really good at predictions, to know to know how to change what we do to respond to the changes in the future.
What caused the atmospheric shift in the middle of the 20th century?
Great question. So the change that occurred is because we have a pressure system in the Atlantic area over here, and this high pressure over here ends up actually redirecting a lot of the weather patterns. So if you watch the radar or the weather events, they often come from the west towards the east, and this high pressure area ends up kind of redirecting them, and so we kind of get this dip often in our weather patterns, or we call it kind of the Gulf Stream, or sorry, so we get a dip and ends up occurring, and so this pressure system shifted south at that point, and so the change in the pressure system ended up kind of redirecting. So we ended up getting more moist air off the Gulf instead of coming in over land. So we now have this Gulf moisture that's moving inland.
Can that pressure system change again? Have we seen it change more than once over the years with the information we know?
We haven't. One of the other really interesting things is that the temperature of the Atlantic Ocean changes the intensity of this pressure system, and so as the Atlantic waters get warm and cool, which ends up changing over about a 30-year time period. So for it to go from warm to cold back to warm, it takes about 60 years. And so we can see over that time period that the intensity has changed with that. So we have these kind of climate oscillations or variability. The one I'm referring to for the Atlantic is called the Atlantic Multi-Decadal Oscillation, and it's kind of similar to El Nino or El Nino Southern Oscillation, which we often hear about, which is for the Pacific Ocean. Yeah. So we have in Alabama here, the two most important long-term changes in our weather in terms of kind of variability over time comes from the water temperatures of the Pacific and the water temperatures of the Atlantic. So from the Pacific, it's the temperature and the oscillation of El Nino Southern Oscillation, and over here it's the Atlantic Multi-Decadal Oscillation.
So these are big scale processes. So this heat transfer in around the whole entire Earth is carried in ocean currents. And so you get heat moving from, and it moves for there are different factors that affect the movement. So pressure, which is affected by temperature and depth and different factors. Excuse me. And so it moves based on these factors, but they're large scale movements, large ocean currents that transfer heat around to different parts of the world's oceans, and then subsequently to the continents and water. So you pointed out over here the elevation. So this is 0.25 meters. This is very, very low elevation. So this is the lower delta, right here.
This whole area is kind of the lower delta.
So the delta is actually kind of defined by this process where the rivers, if you look over here, Steve did point out the difference in elevation here, but if you look at the entire watershed and you think about this in terms of the elevation change between being up in the lower Appalachian Mountains and then down to the coastal plain, and this is Mobile Bay right here. And also look how this is kind of the shape of a funnel. So there's an awful lot of water being funneled into a small area, and then you've got the higher elevation here flowing down towards this lower elevation. And by the time it gets to Mobile Bay, this is pretty low elevation, as Steve has pointed out. So that volume of water will slow in its movement, and then the energy that had been moving this water and carrying sediments along with the water sort of slows when it meets this big body of water and that low elevation, and it deposits sediment. So that sediment that Steve pointed out, that is like, it functions as a sponge, and it is able to absorb a lot of water as compared with other kinds of landforms, whether they're natural, and they're hard like rocks, or whether they're man-made and they're paved. It functions very differently, the way the water will move through, across those different types of land. And as Steve also pointed out, erosion is a compounding factor. So not only do we have sea level rise, but we have, with these kind of loose alluvial sediments in the delta, and then the sandy sediments like on the barrier islands. Not only is the water rising, but as Steve pointed out, it's being eroded. So if you imagine, say you have a pan of water and you make yourself a little island of sand in there, and then you take that and you kind of shift it a little bit, you can see how the sand will shift such that it's no longer kind of mounded up into a form that rises above the water level. So can you tell us where your it looks like a transect right here. Is this the transect for your study site?
Yeah, so all of these markers here are locations where I use data from. And so all of them are long-term stations, mostly maintained by either the Sea Lab with the ARCO stations, which are down here near Mobile Bay, or they're NOAA stations or USGS stations. And so by using long-term data sets that capture mostly the water level and the flow of the water, I can then understand these overall changes. And so by long-term, I mean some of these stations have been in place for almost a century. So the discharge state, or the discharge measurements together now make about 90 years. So we can see those changes. Whereas if we don't maintain those long-term stations, we might only see a few things here and there, and it's really hard to identify if we have any sort of
big
change
picture
in the system. So by using lots of data, I can kind of average it out, and I can look at these different trends that occur, which is what I primarily do for my work here.
Another thing to point out is that a lot of this is in a relatively natural state. So a lot of the delta is undeveloped. So it's not marked by, there are big cities on the edges.
Yes, so Mobile, or like the city of Mobile is here, and you can see kind of these darker areas, and that's all where land has changed. And then over here, this kind of dark spot is the Five Rivers Delta Visitors Center area right there. But otherwise, the land itself has not been changed too much, though there has been a lot of deforestry up in the Delta,
Mm-hmm.
and by removing trees, you actually allow water to flow faster.
Mm-hmm.
So you're kind of reducing the friction up there. And then also, there's a lot of dredging that has been happening in here too. So if you look at this picture here of the Alabama River, just before it comes together with the Tombigbee, you see all these kind of white spots there. And all of this is high areas of sediment that's been pulled out from the river in order to keep it deep enough. And so they want to keep it straight and deep for shipping. But sometimes the river doesn't want to be straight and deep, and so it wants to kind of meander. So there's different areas that become more critical for the dredging, and then you create all these spill piles, and ultimately this can end up changing the flow of the water. So things like the shipping channel that goes all the way down from the Gulf of Mexico all the way up to the city of Mobile. It's about 14, 15 meters deep, and then landward of there all the way up to the Ohio River. It remains about 3 meters, or about
as compared with the average depth of Mobile Bay, which is only about 10 feet deep.
Yeah.
So they dredge quite a deep channel to allow for shipping. Another couple of compounding factors. This is a very complex thing to study. So another couple of compounding factors are the effects of damming rivers. So the movement of water through rivers that have been dammed, and the movement of sediments through rivers that have been dammed can affect these different, the elevation and the water flow. So a lot of different complexities to look at.
Yes. And not all dams are the same either. So some dams hold back all the water, and some dams hold back the water until it reaches a critical point, and then it just spills over the top. And so it can completely change how much sediment might get stored and not get stored too. So you have to know kind of what the dams are doing upstream in order to know whether the response in watching the flooding is because of dams, or it's because of the natural process that's occurring.
So the United States Army Corps of Engineers has been sort of altering these river channels for at least 100 years. I'm not sure how much longer than that, in order to allow navigation. But in that time, they've learned a lot. We have learned a lot about the different sort of down current in time and in space effects of these sort of engineering, these environmental engineering projects. So what is it that sort of the big picture takeaway from your research? Kind of wrapping these different factors together.
Yeah, I think one of the main big picture things is that in these transitional areas from the sea all the way inland to where we have a normal river environment is a long transition, and if we only look at one aspect of it, we only get a small part of the story, and we don't even get the part of the story that covers how that area is even disturbed. And so really we need to look at the entire transition to understand what's happening in those smaller regions along the way, or else it can easily be kind of misinterpreted in that process.
So with data the kinds of data that you are assimilating, then people who are, for example, city planners or restoration specialists might use that information to manage the land use or restoration projects. So if they can understand sort of what this looked like historically, how it's changing, how we might attempt to return it to a natural, a more natural state, or for example, locate developments in a place that's more advantageous, less risky. So these are the kinds of products that might come from.
Yeah, and actually one of the kind of results of this work is that it's helping to inform the Food and Drug Administration on how to regulate seafood at the coast.
Wow.
Because river events, when they flow down to the sea, they can bring contamination. So, oftentimes it's natural, not always, but this contamination can cause things like shellfish to also be contaminated, because they just simply are filter feeders and they eat whatever comes through, and so understanding when the contamination is going to come, and also how much contamination is going to come is needed to better manage the shellfish industry.
So they can predict and then target their efforts, because they can't test everything everywhere, but if they can use this information and predict where their efforts might best be targeted, then it's more efficient for them to do their testing. Interesting. So is there anything else that you would like to share, or any other kind of important takeaways that you think folks should know from this work?
I can talk for hours about my work, as anybody can, but for the moment I will just leave it at that.
Well, thank you for sharing with us, and thank you for joining us this morning. We have our Boardwalk Talks on the 1st and 3rd Wednesdays, and we hope you'll join us for the next one.